One of the most powerful statistical machine learning algorithms available for binary classification is the logistic regression. The aim of the logistic regression is to classify different set of samples into classes based on the attributes or the features that the data has. In this video, we will be breaking down the simple concepts of logistic regression and learn how they are relevant to us for the task of binary classification. Before starting with this video, I would suggest that you should get familiar with the concepts of linear regression. If you're not already familiar with the linear regression, then in this playlist, I have done a video on linear regression. So I would suggest that you go and check it out before you get started with logistic regression. So logistic regression, unlike its name, is a binary classification technique and is used to predict class labels for a given set of samples. Instead of predicting something which is a continuous value, for example, weights of a student in a class, it aims to predict something which has only two possible outputs, like yes or no, or true or false, etc. So one of the examples for classification problem could be based on the past history of various patients who have either diabetes or they don't have diabetes. For a new patient, I want to figure out based on his test results whether he has diabetes or not. Logistic regression is one of the algorithms that is aimed at predicting class labels when there are only two possible choices. So assume that you have a data regarding the weights and BMI of students of class. So assume that we can plot this data on a graph and assume that on the x-axis I have the weight and on the y-axis I have the body mass index. So the task of the linear regression is to fit a straight line that passes through the data and gives me the approximate BMI for a given value of the weight. However, in this case, I have to predict a continuous value, which is the body mass index based on the weight. However, I can transform this problem into a new problem, which is basically I want to figure out whether the person is obese or not based on his weight. So one of the possible solutions to this problem is by fitting a straight line similar to linear regression. So in this case, using the weights as features, I will predict a continuous value between 0 and 1 by fitting a straight line. However, there is a problem with the straight line fit for the binary class dataset because the linear fit will either be an increasing or decreasing function of the input variable, or in this case, which is the weight. And as the value of the input variable increases, the resulting fit will grow very large and will give me unexpected results. So in order to tackle this, I want to figure out a function which is bounded between two possible values, which is either 0 and 1 or minus 1 and 1. Why? Because I can transform the value yes to the value 1. Similarly, I can transform this value no to the value 0. Similarly, I can also map these values to either yes to 1 again and no to minus 1. And hence, I want to figure out the function which is bounded between two specific set of values. So without the loss of generality, let us assume that no is mapped to 0 and yes is mapped to the value 1. So I want to figure out a function which is bounded between 0 and 1. So I can also proceed with the function that is represented by the yellow line, which is giving me the value of 0 for weight less than 75 and value 1 for the value of weight greater than 75. However, this function is tough to deal with mathematically, and hence I would prefer a function which is of this form. And this function is mathematically very nice and is simple to deal with. So this function is known as the sigmoid function, and it is a mathematical function that transforms any real value between 0 and 1. So mathematically, sigmoid function is defined as sigma of x is equal to 1 over 1 plus e to the power of minus x. And if I present it on a graph, it can be drawn like this. So it is a function that is bounded between 0 and 1. And as the value of x goes towards infinity, the value of sigma x goes towards 1. Similarly, as x goes towards minus infinity, the value of sigma goes to 0. So sigmoid function has very nice mathematical properties, which makes it suitable choice in various machine learning algorithms. Since it transforms the values between 0 and 1, it allows the output to have probabilistic interpretation. So let us see how the logistic regression works with the sigmoid function. So first we take any input x and then using this input x we regress on it with the help of linear regression by the function f of x is equal to w0 plus w1 x1 plus w2 x2 plus till wd xd, and hence with this regression we get the value z hat. Further, this z hat is mapped in between the 0 and 1 by the help of the sigmoid function as y hat is equal to 1 over 1 plus e to the power of minus z hat. So this allows us to modify code x to the value y hat, which is in between 0 and 1. So now let us see an example. For instance, assume that we have x is equal to 1, 2, 3. So first we regress upon the x using linear regression as z hat is equal to f of x is equal to w naught plus w1 into 1 plus w2 into 2 plus w3 into 3. Assume that we have w naught is equal to 1, w1 is equal to 0.5 and w2 is equal to w3 which is equal to 2. So using the value of these weights, we get z hat is equal to 11.5. Now we apply the logistic function, which is basically the sigmoid function on z hat to get y hat is equal to 1 over 1 plus e to the power of minus 11.5, which gives us the value 0.999. Similarly, we can transform any input x with the help of logistic regression by first regressing it over with the help of linear regression and then applying the logistic or the sigmoid function on the regressed value to get the probabilistic interpretation. So now the main aim of the logistic regression is to figure out these parameters w0, w1, w2, w3 till wd such that this y hat is the best possible outcome for the value x. So similar to linear regression, we test our model based on some loss function. So in order to evaluate the goodness of the model, we test the predictions using an error metric. Due to the discrete nature of the output variable, mean squared error is not a suitable choice for the logistic regression fit, and instead we have something called the binary cross entropy loss function. So this binary cross entropy function works well with the sigmoid outputs, and this ensures that the probabilities are properly compared with the true values. So now let's see what this binary cross entropy function is. So it measures how well the predicted probabilities match the actual labels, which are actually 0 or 1. So for a sample x with logistic regression predicted value y hat and a true class label y, we compute the binary cross entropy loss function as L of y hat comma y is equal to minus y into log y hat plus 1 minus y into log of 1 minus y hat. So now let's see why this binary cross entropy function is a good measure for evaluating the logistic regression error. So for instance, assume that y was actually 1 and y hat is close to 1. So in this case, this value will become 0 and hence we will only be dealing with this value. So when y hat is close to 1, log of y hat will be close to 0 and hence the value of the error will be less. Similarly, if y was 0 and y hat was close to 0, in this case, this value will be 0 and then this value will be the only thing that will be part of the error. And since y hat is close to 0, log of 1 minus y hat will be close to 0 again. So in this case, again, the loss value will be less. On the other hand, if y was actually 1 and y hat was close to 0, so only this term will be taking presence and hence as y hat is close to 0, this value will be very large. Similarly, if y was actually 0 and y hat is close to 1, again this value will be 0 and this value will only take part in the error and hence again log of 1 minus y hat will be very large. To minimize the total error, we will try to minimize the value in such a way that y hat is close to the true value y. Now let's see what the binary cross entropy function is for the total dataset. So for the complete dataset D, which is equal to xi yi, I is equal to 1 till n, binary cross entropy for the whole dataset is computed as minus 1 by n summation I is equal to 1 till n yi into log of yi hat plus 1 minus yi into log of 1 minus yi hat. So by the similar reasoning, it will penalize the bad predictions much more as compared to the good predictions, and hence as the value of the predictions grows better, the loss function will go towards 0. So this is the idea behind the logistic regression. However, unlike the linear regression case, we don't have a closed form solution for figuring out the parameter values of w0, w1 till wd for the logistic regression, and we require numerical techniques to optimize this loss function to get the best set of parameters.